Hello, everybody. My name is Jeff Tackes, here with Gellert Toth. We worked on the Caterpillar tube pricing. It's a Kaggle competition for our final project. Our team name was the NW Data Science Regressors. First, let's talk a little bit about the Caterpillar company. So Caterpillar is one of the largest construction equipment manufacturers in the world. In 2017, the Caterpillar company grossed over $45.5 billion. They have a variety of huge construction and mining equipment stations all around the world. They were originally founded in 1925. They can be traced back to a merger between the Holt Manufacturing Company and the CL Best Tractor Company. They created the Caterpillar Tractor Company in 1925. In 1986, they rebranded to their current name, Caterpillar Inc., and they are a Fortune 100 company. So the purpose of the Caterpillar competition was to try and predict future quote pricing for their tubes. Why tubes? Well, the mechanical equipment that Caterpillar uses rely on several complex tubing networks to ensure that the equipment do their job properly. Each tube has their own set of unique properties and characteristics. The tubes differ in dimensions, materials, number of bends, radius, bolt patterns, volume, length. They have many different features for all the different tubes. And to better predict costs, Caterpillar started this competition to try to find an algorithm that can take all these unique characteristics and historical quote prices to try and predict future quote prices. So a little bit about the data set that we were given. So the data set consisted of a training table, a training table and a test table. In the training table, we had over 30,000 records as we did in the test table, with 8 different variables. However, there were 20 other tables that we were given for this competition. You can kind of see an ER diagram down at the bottom. The fields are not really legible, but it'll show a little bit of the complexity that this competition involved. The vast majority of our time was actually spent just trying to figure out the relationship between all the different tables and pull the information from all the tables into our program. So once we merged all the data, we ended up with 60,448 variable or observations with 1,154 variables. So it's a very, very, very wide data set. Several of the variables, over 200, were actually all NA values. It's completely blank. In addition to those 200 variables that were completely blank, there were several others that had a large proportion of the observations as NA values. So another major hurdle in this competition was overcoming or figuring out how to handle all of the missing data. So as to how we got to 1,154 variables, the main reason was that so every tube assembly has a bill of material, and all the bill of materials have 8 different components that make it up. So you can kind of see that as the third table over here to the right, the third table left, called the bill of materials. They have 8 different components, and those 8 different components are then connected to all the different component tables, which are pretty much all the tables to the right. So there was over 66 unique characteristics to every single component, with 8 components making up the bill of materials for each of the different tubes. Once you merge all those variables together, it starts becoming you start getting a very large number of predictor variables in your data sets. As for transformations that we performed on our data, so the graph on the left shows the graph of the cost, which is our dependent variable. It's what we're trying to predict, obviously. You can see it's very skewed to the right. And so we wanted to try to normalize that a little bit. So we took a log transformation on the data just to kind of spread it out and make it a little bit more resemble a normal distribution. So you see the transformed log cost variable off to the right. Other data preparation. So this competition was very much about feature engineering. The data that we were provided, it didn't really give us a lot of predictive power in its raw format. And so we tried to pull out as much data, as much predictive power from the data provided as we could. So one of the features that we created was a whole bunch of data attributes. So they were just giving us a quote date, a normal day, month, year quote date. And we tried pulling out the month, day, year, day of month, day of week, day of year, week of year, to see if there's any seasonality or any type of fluctuation in prices that correlated to the dates or date features. Another feature that we created was the volume, and so we were given the diameter of some of the tubes, and so from that we were able to create a volume variable, as well as aggregate numerical data. So the table at the bottom right shows all the different component numerical data. So it gives us the quantity, the adapter angles, overall length, et cetera, et cetera. And so all these variables existed for all the 8 different components that made up a bill of material. And so instead of just keeping 8 separate numerical variables for every single one of these, we created 4 aggregate variables for each one of these. So we created the min quantity, the max quantity, the mean quantity, and the sum quantity. And same thing for adapter angle, the min, mean, max, and sum. So we created those 4 aggregate variables for all of these different numerical variables, and then we just dropped these variables out of our data set. So we just kept the aggregates. As for model building, we mainly stuck with 3 different models, random forest, a regular gradient boosted model, and an XG boost, extreme gradient boosted model. The random forest model originally scored pretty decent in the grand scheme of things. We scored a 0.24 RMSLE score, which actually was a pretty good score, but in retrospect to the rest of the competition, it didn't even get us in the top 70 or 80%. It was towards the bottom of the competition. Then we started the XG Boost model, which showed an incredible increase in performance. The random forest model was first very slow. It took a few hours to run the model the first time we did it. Then we had to implement the H2O package in R, which did increase the speed quite significantly. But the XG Boost model right off the bat performed much quicker and much better than our random forest model. As for the metrics in the model, the competition metric in the model that was used was the RMSLE, which is the root mean squared logarithmic error. Formula is down below. It's pretty much the RMSE, only with the log thrown in there. As for how the competition was graded, they had 2 different data sets. So they had the private leaderboard and public leaderboard. The public leaderboard was made up of 30, your scores were judged on 30% of the test data, and the private leaderboard is made up of 70% of the test data. Ultimately, the private leaderboard determined the final winner. This competition did have a cash prize of $30,000 split between the top 3 models. So the private leaderboard was that deciding factor in who won the competition.
Okay, so I'll take the next couple of slides from Jeff. Let's talk a little bit about model selection and results. So what you see here is a couple of thoughts about the model, our winning model. So obviously we were using XG Boost, and what's really nice about this technique is that it allows us to, or it allowed us to change or tune some parameters. There's a general parameter that's called booster, which we set to GB3, and we also specified the objective function to be reg linear. The tree booster should get superior results versus linear booster all the time, according to some documentation we read. We also specified some booster parameters. We had to look at the learning rate. So the learning rate by default is 0.3, but we tuned it to a much lower rate to 0.005. Then there were some other parameters, such as the sum of weights, which was supposed to control overfitting. We set that at 5, and there was also a parameter called maximum depth, which we set at 6, and the maximum number of features we set that at 0.6. So if you go to the next slide. here you see the results of the winning model. So when you run XGBoost, you basically get four different columns pertaining to each of the features. And so the most important one is the gain, which essentially is the importance. It depicts the importance of an actual variable. So it is the relative. It actually shows the relative contribution of the predictor. So what's really interesting about this is that the top two, which is quantity max and quantity mean, were by far the two most important variables in terms of the gain or importance. And if you compare those figures to the annual usage, you see a significant drop-off at 0.06. And then if you start looking at the other variables, you start seeing a very significant drop-off. And here we are just showing the top 20. But as Jeff was talking about earlier, we had hundreds of these. So you can imagine that by the time we would get to the last variable on the list, it would have a very small gain, or it would have a very small importance. So if you go to the next slide here, here's a comparison of the random forest model and the XGBoost model that we played with. So there are a couple of statistics in terms of the performance of the models. You can see the MSE, RMSE, RMSLE of the random forest model. So what's really interesting about it is that the winning random forest model had 2,000 trees, but then again it had a score of 0.246. So that's the RMSLE score. And as Jeff stated earlier, that score looks pretty good on the grand scheme of things. But when you look at the ranking that it afforded us, it put us into towards the very bottom of the competition. I think we were in the 70th percentile or even lower. So we then switched gears and we started looking at XGBoost. So here you can see a couple of statistics about about the model. So you can see the train MSE and the test MSE, as well as the train and test RMSE. And as I described earlier, we tuned some of the parameters. We also ended up using 20,000 rounds during the algorithm, during the creation or the running of the algorithm, and that gave us an RMSLE score of 0.21. So that was a significant improvement. So it was really interesting, and numerically speaking, if you compare the 0.246 to 0.219, numerically speaking, there is hardly any difference. But in terms of the placement in the competition, this put us into the very top part of the, in fact, in the top 10 in the top 10 percentile. We had a rank of 116 out of the 1,300 or so competitors. So there was we looked for some articles in terms of what could be the reason for XGBoost being a successful model, and what are the advantages of using XGBoost in general. And these are six things that people generally talk about. So the first most important one is that overfitting is much less likely using XGBoost versus any other type of tree-based model, and that's because during the regularization, the model uses a penalty, which a penalty when we add more and more features into the model. So that helps us overcome overfitting. The other thing that's interesting about XGBoost is that it has a sequential nature, just like any other boosting, but XGBoost was designed to use all the cores of the computer during processing. So as a result of this, it's a very fast method, and it ran in just I wouldn't say a couple of minutes, but in comparison to the random forest, which sometimes ran 4 hours, this was a a significant improvement. The other thing that's a really big advantage of XGBoost is that it allows us to tune the parameters, and it is the tuning of the parameters that helped us increase our RMSLE scores. In fact, without it, at first we had a pretty poor score, but once we started playing with these parameters, we were able to achieve a pretty nice score and increase and make our rank much higher. And the fourth item here is really important when it comes to our specific data set, which is the caterpillar data. As Jeff was talking about earlier, we had tons of missing data in many of the variables. Some variables had up to 80% of the data missing. And so XGBoost has a really nice capability of handling missing information. The fifth item here is the discussion about boosting being a greedy algorithm. But what's really nice about XGBoost is that the XGBoost allows or gives us the ability to specify the maximum depth of trees, and then it starts pruning backwards, and it removes unacceptable splits. So that helps with overfitting. And the sixth item here is that XGBoost has a built-in cross-validation scheme. So as you are tuning your parameters, you can do so by cross-validation, by doing cross-validation. So the final discussion points here is that as we were going through the competition, we spent quite a bit of time, a lot of time on pre-modeling. So as Jeff alluded to it, we had a lot of time spent on understanding the data. We had 20 tables. The tables were incredibly complex, and to figure out how they connect with each other was quite a bit of work. Then we started looking at looking at the variables that resulted in after linking the 20 tables, and we had a very large predictor universe. So we had over 1,000 predictors in the data set. So the task is to find or to kind of squeeze some value out of as many predictor variables as possible. And in order to even do better than just using the regular predictors that were given to us, we then got involved with feature engineering, which took a lot of time. So to figure out, how to create features, in terms of the time or the volume, or create a minimum and maximum and average values of these predictors, it took a lot of time to do. As far as the modeling is concerned, the modeling didn't take that much time. So obviously it was less than half of our time was spent here, but to figure out which was the best model, or which was the best type of model to use was a challenge. And then finally the discussion that we had about tuning the parameters or tuning the models is also obviously that was also a very very challenging task. And in conclusion, we just wanted to show you our placement. So unfortunately, the competition took place a couple of years ago when it was closed for entry, so we couldn't enter our score. But you can compare our score to the leaderboard here. So our score of 0.2182 gets us right above the random Forrest Gump, who was at the time ranked 116th. So we did a tiny bit better than the random Forrest Gump, and a little bit behind Patrick Chan. So if we were to if we did this project at the time of the competition being open, we would have scored 116th place.